Today we start chapter 7, and this entire chapter deals with the topic of confidence intervals, and the bulk of the material is all in this section 7.1. Then for 7.2 and 7.3 we just make small changes, and then we still are using confidence intervals. So basically one idea we need to know for chapter 7. So let's take a look and see how these work. Well, statistical inference uses results of samples to make decisions and draw conclusions about the population from which the sample is drawn. And chapter 7 covers a type of statistical inference called estimation. We will develop techniques for estimating values of population parameters based on values of corresponding sample statistics. There's a little note here. If you notice up here, it says estimating the mean when the standard deviation is known. So this would be a situation where we are looking for the population mean. So in other words, we don't know the population mean, yet somehow we know the population standard deviation. Well, this is really unusual. So normally, if you know this population standard deviation, you will typically know the population mean. So it's typically taught this way, even though this is sort of an unlikely situation. This situation is much easier to understand. So usually when you study confidence intervals, you first study this case. It's unlikely to see in practice, but we study this case first because it's the simplest case, and then in 7.2 and 7.3 we'll tweak this so they'll be more realistic. But once we understand how confidence intervals work, then it'll be easier to adjust to those two. So that's what this note is going to say right here. So then the note is that most of the time, when mu is unknown, sigma is also unknown. And this mu, remember, this is this Greek letter mu, so you have to be careful. We don't want to, sometimes students are a little too sloppy with it and it looks like an M. And we have to be careful with our symbols in math, right? Because they all have meanings. So we need this Greek letter mu. It's like a U with another little arm on it here. So when we're talking about mu, we want to make it really clear. So you don't want to put something that looks like an M, because it'll just add to confusion when you're trying to express your ideas. So to get started here, we start with a point estimate. And a point estimate is a single number used to estimate a population parameter. So let's say, for instance, we want to know the population mean for the age of a GRCC student. So we're going to know basically the average age of a GRCC student. We don't know it. So we take a sample. Let's say we sample 100 students and we come up with a sample mean. So this number would be a point estimate. So x bar is the point estimate of mu. And then p hat, that's the point estimate of p. And we'll talk a lot about p hat and p in section 7.3. Up until now, we've just sort of mentioned it. If you were working for a polling organization and you wanted to know what percentage of voters are going to vote yes on proposal C or whatever, you would want to know P, the population proportion of voters who are going to vote yes, but you can't find that. So instead you take a sample and you find P hat, which is the sample proportion of voters who are going to vote yes on proposal C. So we'll talk about these a lot in section 7.3, but these would be point estimates. So this number is just a point estimate, but what we're typically going to do is we're going to build an interval of values to try to estimate this. So we're not going to estimate this with just and say we think it's 27.6 or close to it. We're going to use 27.6 to build an interval of values and then make a statement about what we think this is based on that interval. So when using x bar as a point estimate for mu, the margin of error is this number here. Now, if you look, this is the absolute value symbol, right? So the margin of error is just the difference between x bar and mu. So x bar is 27.6. Mu, we don't know what it is. But the margin of error is the difference between these, this unknown number and this number from our sample. And the interesting thing about what we're going to be able to do in Chapter 7, seems like we couldn't do it, but we can actually put a bound on this margin of error using confidence intervals. So even though we don't know what this is, we just have this sample, we're going to be able to say the difference between these is less than 4 or whatever, just making up a number, an example. But it seems like we couldn't do that because we don't really know what the mean is, the population mean. We don't know it, right? We're taking a sample, but using confidence intervals, we will be able to put a bound on the margin of error, which is the difference between our sample mean and the true population mean. So you'll see how that works as we go here. But the margin of error is just this difference, the difference between our sample estimate and the real mean. So to do this, we use something called the confidence level. So the reliability of an estimate will be measured by its confidence level. So suppose you want a confidence level of C. Now usually C is going to be one of three things. It could be literally any number, but usually it's going to be 0.90, 0.95, or 0.99. These are the three we'll almost always see. So this is going to be something that we kind of know about. We just didn't see it in this context. But let's say we've got, to see how this works, let's say we've got a standard normal curve here. So if we want a confidence level of C, which is usually going to be one of these, it's just the area underneath here. So if we go, just make something up here, about like this, and we want this shaded area. Well, this shaded area will be C, which would normally be one of these. So let's say C is 0.95. If we want 95% of the curve to be shaded, then we know roughly, isn't it true that if this z-score is -2 and this z-score is +2, we'll have roughly 95% of the area shaded here? So that's kind of what we're getting at here. So this right here, this is a standard normal curve. Right, it's standard normal, which means it has z-scores. So this right in the middle, this would be a z-score of 0. And this is z sub c, and this is negative z sub c. And I'm going to actually move this over because it would be symmetric, right? This is going to be a symmetrical curve, so we've got a 0 there. So this confidence level, if we point to this, we could say this is confidence level C. And again, C will typically be one of these, but it could be anything. But this is what you typically see. Confidence level C and corresponding critical value Z sub C. So here's our new phrase, critical value. The critical value is just a z-score, that corresponds to one of these. So z, we know already, right? If z sub 0.95, the z-score corresponding to 95% of this being shaded, well, we know roughly it's going to be 2, right? Because if that's a -2 and a +2, 95% will be shaded. If we had a z-score of 0.68, if 68% here was shaded, wouldn't this be like -1 and +1, right? So it's the same thing that we've talked about before, but it's just, we're going to call it a different thing here. So the critical value is just a z-score that corresponds to this level C being shaded. Okay, so it's something we've seen before. It's just, I guess it's a little bit different context, but same idea. So this is just saying that the area under the normal curve from negative z sub c to z sub c is the probability that the standardized normal variable z lies in that interval, which we've already seen, right? Between -2 and 2, if you have this shaded area between -2 and 2, we know that if you randomly choose a z-score from a normal distribution, there's about a 95% chance it's going to be between -2 and 2. So that's all it's saying here. The probability that this z-score is between these two critical values, so let's say this is a -1 less than z less than +1, then this is going to be 0.68, right? So it's just stuff that we already know about this standard normal curve. So for this one, let's say we want to find this critical value, the z sub c, such that 99% of the area under the normal curve lies between -z sub c and z sub c. And this is just another way of saying that. So for us to do this, we could take our standard normal curve. So we've got our standard normal curve here. And we want this to be, that's a little bit of an ugly looking curve, but let's just make it work. So we want this to be set up so that we've got 99% of that curve shaded in. So we've got like here and here, and this is all 99% shaded, 0.99. Well, if 0.99 is shaded, that only leaves us 0.01 that's not shaded, right? If 99% of the area under this curve is shaded in, then only 1% is left, and that's going to correspond to these z-scores, right? Here's z sub c, or negative and positive. There's only 1% left to go here and here, right, in these two little spots here. So to see in each spot, we'd have to even cut this in half. So we cut this in half, and we get 0.005, which means that there's this little part here, there's 0.005. And over on the other side, there's the other 0.005. So they want us to find the z-score such that 99% of the area under the normal curve lies between -z sub c and z sub c. So we already know how to do this. We've seen it before, right? We used inverse norm to do this. So on the calculator, we would go like this. We'd say inverse norm. And we just have to remember, when we looked at this command, inverse norm by default always starts from the far left, and it goes this way and keeps adding up the area. We're going to give it an area, and it's going to give us a z-score. So inverse norm, we plug in an area, it's going to give us a z-score. And what we talked about before is some of the newer calculators can tell you start from the left, the right, or the center. So if you have the newer calculator where you can tell it to start from the center, you can just put 0.99 and tell it to start from the center. But most of us, by default, inverse norm starts from the far left, so it's going to start way back here. And it's going to keep adding up areas until we get to until it gets to the area that we give it. So if we wanted to get one of these z-scores, we could just punch in 0.005. 0.005. And we covered this in class before, so just thinking chapter 6, probably section 6.3 or so, we did the inverse norm. And it's under the distribution, so on your calculator you would go second vars, right, to get to all the distributions. And the third one down is inverse norm. And we just punch in 0.005, and it gives us this number. Now I'm going to round this to the second decimal place for a reason you'll see in a second. Negative 2.58. Which means that that is negative 2.58, which means that this is going to be positive 2.58, right, because of the symmetry. But if you wanted to verify, you could go all the way to that one just by adding all this up. So if you do inverse norm 0.995, you'll get this z-score over here, which would be a positive 2.58. So this is one way to do this. And just to verify, let's check this real quick. What should we get if we do this? If I go normal CDF, negative 2.58, positive 2.58, just to verify even this statement, right? Negative 2.58 to positive 2.58, I should get roughly 0.99. We're just doing the fact that these are inverses of each other. Here I plug in an area, it gives me z-scores. Here I plug in z-scores, and it should give me an area. And sure enough, if you plug this in, you get roughly 0.99, right? It's approximately 0.99. So because these numbers that we talked about before occur so frequently, there's actually a little table. In fact, it's all over the book. So one way you can do this is with a calculator, but it's actually more work. So let me do it this way. We'll say number one, you can do this with a TI-83 or 84. And number two is with table 7.2. And I'll show you a picture of it in a second here, but it is on page 362 in the book. It's in page A23 in the appendix. It's in the inside front cover. It's all over the place. So if you look inside the front cover, or basically wherever in your book, wherever the table is for the normal distribution, you'll see this little table next to it. So this just shows us these critical values, or the z-scores for various levels of confidence. And the ones that we see all the time are the 90%, which has the z-score here, and also 95%, and then the 99%. And this one that I mentioned, we know that 95% is going to be around 2, right? Because when we studied section 6.1, we said about if you have a z-score of negative 2 to 2, or if you're 2 standard deviations below the mean to 2 standard deviations above the mean, you get about 95% of the data. It's a little different here because we were rounding when we said 95. So, but it's close to 2. So these are the 3 that we'll see over and over again. So in chapter 7, we're going to always have these z-scores of, or these confidence levels of 90%, 95%, or 99%. And you could go through the process we did back here with the calculator, but just easier to look here. And by the time you're done with chapter 7, you'll pretty much have these three memorized because they come up repeatedly. So just make sure you can find this table. And actually, of course, you don't need the table. You could use a calculator, but it's much easier because these come up so often just to know where this table is. So look, wherever you see the standard normal curve in the book, any of the tables, or the spots that I mentioned before, you should be able to find this. Okay, now comes the part where we get to do a little algebra, and we'll make this quick and painless. But I know if I just gave you a formula, you guys would be like, oh, now wait a minute, Kurt. I would really like to know where that formula came from. So just getting ahead of the game here. I want to just go through this and develop this formula together. So this is something that we don't, you don't really need to know exactly where this came from, but we'll just walk through it real quick. It's not too bad, just a little bit of algebra. So we start off here with something that we just talked about. For a confidence level of C, we know that this is true. So C, just to make an easy example, if C would have been 0.68, we know if this is -1 and this is +1, that would work, right? So generally speaking, we have this. Also, we're gonna use x bar to approximate mu, right? We're gonna use our sample mean to approximate the population mean. And the x bar distribution has mean mu and standard deviation of this, right? Standard deviation divided by n. We saw this in section 6, basically 6.4 and 6.5. So we convert x bar to a standard score or z-score using this formula. Again, this is the one we saw in 6.4 and 6.5. So what we can do then is in this formula here, swap out this z with this, which gives us right here. So we go from here, swap out z, and now we have this. And now, you guys know how much you hate having these complex fractions. So we're going to get the fraction, we're going to get rid of this fraction by multiplying all three parts of this compound inequality by this denominator. So if you're in algebra, you would say, okay, I'm going to clear up this fraction by multiplying everything by that denominator. Right, and you multiply this thing by the same denominator because then it will cancel that. Then you multiply this. So by the time you get to the next step, basically all three parts of the compound inequality are multiplied by the denominator to get rid of that, to make it cancel, so it goes away. So then at this point we can notice what this says. This says that the point estimate differs from the population mean by this maximal margin of error E. And it's saying, okay, this thing right here, this would be E, because this is just negative E and positive E. And we're basically saying that the the sample mean minus the population mean is going to be less than this, and it's going to be greater than this. So this is our maximal margin of error right here. Now also we still want to try to get this mu isolated. So what we should do first to get this isolated is we're going to subtract x bar from each side. Right? So subtract x bar from here, and from here. When you subtract it from here, it just goes away. So you have, if you follow this down here, you just have negative mu. Then you notice there's a negative x bar tacked onto each of these. But of course, if we're trying to isolate mu, we don't want the negative, we want the positive. So what we're going to do is divide each side by -1. Okay, the software is doing its thing again. Where would it go? Okay, here we go. So you divide each side by -1. So divide each of these parts by -1, right? So of course, this will become a positive mu. And if you remember from the good old days in algebra, when you have an inequality and you multiply or divide by a negative, these reverse direction, right? Of course, these signs all change here because you divide by negative, so you get here. And now we're really close, but whenever you have a compound inequality, you always want them pointing to the left because that puts the smallest number on the left. So we basically just flip these around. We use the symmetry to get here. And now we're really close, but we're going to swap out E again. This is big E, right? Just like this. So I've got this here, and we have this. So this last equation is what we're going to be calling a confidence interval. So we're looking at this. It says that there's a chance C that the interval from x bar minus E to x bar plus E contains the population mean mu. We call this interval a confidence interval for mu. All right, so that's the algebra. That's where this comes from. You really don't have to know the algebra behind it, but I know you would want to know. So we go here. I gotta tell you, you guys are so lucky because the first time I taught this class, I had taught calculus most of the time, and I started teaching statistics. In calculus, there's a lot less words, so you take a lot of notes just right off the board. And in statistics, there's so much more writing that I saw like pain like in my students' faces when we did all this by hand on the board, and they looked so sad. I felt terrible, felt guilty. Felt like I'd put them through a faculty meeting or something. That's how bad it was. So it's much less painful this way, and we just sort of jot these ideas down, do a little algebra, and we come up with this confidence interval. And really, if you've never seen a confidence interval before, it doesn't really make sense until you start using these. So yeah, we have that confidence interval, but it really, until we do a couple problems, it's not really going to make much sense. So that's where we're at. We have our interval. It is right here. We basically have the formula for everything we need to find a confidence interval. Now we just have to figure out how to find them, and then more importantly, how to interpret them correctly. It's really easy to interpret them incorrectly. So that's what we'll work on next. So we've got our information here. We're looking for a confidence interval for the mean when sigma is known, the standard deviation is known. And we've got our interval here. We build it using this error, our maximum margin of error E. We calculate it here and then plug it in here. We got a little note here. It says if the x distribution is normal, then any sample size n will work. If x has an unknown distribution, then we need a sample size n greater than or equal to 30, and that is from the central limit theorem, right? Because if we are sampling from a normal distribution, then our sampling distribution will be normal no matter what. So if the x distribution is normal, any sample size will work. And then if you remember, if x has an unknown distribution, then we need a sample size to be greater than or equal to 30. So I mentioned in the earlier video, 30 is our magic number, right? So we need to always make sure we have a sample size of 30 or more, because if we do, then the x bar distribution will be normal. So when we plug in this x bar, right, we'll know that this sample mean is coming from a normal distribution, right? So if it's coming from a normal distribution, we take the mean of a sample, then we know that, for instance, 95 out of 100 times that x bar will be within 2 standard deviations of the mean, right? So that's kind of why we're always checking this. So example 2 on page, or for us is example 2 in the notes, page 370, number 12 says, suppose x has a mound-shaped distribution with sigma equals 9, and it says a random sample of size 36 has a sample mean of 20. So it says check the requirement. Is it appropriate to use a normal distribution to compute a confidence interval for the population mean mu? Well, sometimes the author will say something like, suppose x has a mound-shaped distribution, which sounds like, well, maybe it's, mound-shaped and symmetrical enough to be normal, but it really doesn't even matter because of right here, sample size 36. So it says, is it appropriate to use a normal distribution to compute a confidence interval for the population mean mu? Yes, because of this, right? Sample size is 36. So if we hit this magic number, then we're okay. We know that our X bar distribution will be normal. If we don't hit this, then we don't know unless we know we're sampling from a normal distribution. So I don't like this wording like this because it seems like a gray area, right? Because it seems like, well, maybe they're saying it's mound shaped enough to be normal. So I wish they just wouldn't have said that, because then it makes it clear, okay, we're still okay because of this. But when there's a small sample, like if this had been a sample size of 8, they would have to say X has a normal distribution, or X is approximately normal, or something like that. So even though this seems a little gray when they say it like this, it doesn't turn out to matter because of this. We hit the magic number of 30 or more. So check the requirement. It says, is it appropriate to use a normal distribution? And yes, it is. We can say yes, since n is greater than or equal to 30, right? Because n is 36. The central limit theorem says that the X bar distribution will be approximately normal. And also sigma is known. So we'll find out in the next section that if sigma isn't known, then we have to do something else. But really all we need to worry about right now is we've got a sample size of 36, so we are okay. So then it says find a 95% confidence interval for mu. And this is where we're going to use this formula. Basically, every time it says find a confidence interval, we're going to use this formula. So to use this formula, we need to find E. So we've got, make a little room here, 95% confidence interval for mu. Well, we need this. X bar minus E is less than mu, which is less than X bar plus E. And E is equal to Z sub C, sigma over the square root of n. Okay. So Z sub C, well, that's just our critical value, and it comes from 95% here. So every time we have one of these problems, they're going to put a percentage down here. We already talked about it's normally going to be either 90, 95, or 99. And then we have to look at that little table, right? So if you look at that table that we just talked about, and you look for a 95% confidence interval, you get the z-score there, which is going to be 1.96. So it's right over here, confidence level. They want a 95% confidence interval, so that's a level of confidence 0.95. We look right here, 1.96. So 1.96 is the number we're going to use for our z-score. So we have E equals 1.96, and sigma, it said, was 9. The square root of n, well, n is the sample size. In this case, it is the square root of 36, right? So that gives us 1.96, and there's 9. The square root of 36 is 6. So we can just punch this in the calculator at this point. I guess you can clean it up a little if you want to, but once we punch that in the calculator, we are going to get roughly 2.94. So actually we get exactly 2.94. So we've got our maximum margin of error E, which is 2.94. So here's our formula. 2.94 is going to go for E in both of these cases. And X bar is our sample mean, which they told us was 20. Because the original problem said a random sample size 36 has a sample mean of 20, right, in the original problem. So there's going to be a 20 here. So at this point, we just plug in the numbers and see what happens. So we plug this in, we do the math, we get 17.06 is less than mu, which is less than 22.94. And in the book, when you look in the back of the book, a lot of times they'll write it like this. Okay, so the book does it that way. I like this way better because it tells us what we're approximating, right? We're trying to approximate the population mean. And this is our confidence interval. So calculating the confidence intervals is the easy part because they always come from this formula right here. And x bar is given. We just have to calculate e and then fill in the blanks. And then our answer looks like this. So finding the answer is the easy part. The hard part is interpreting what this means. And this takes a little practice to really understand what this means. So I'm going to write down our interpretation and then we'll talk about what it means. Because I want to explain the meaning of this confidence interval. So here's our interpretation. We could say this. We are 95% confident that the interval, I'm just going to write down the interval, is one that contains the population mean mu. Okay, so what this means is, first, we are 95% confident. This is actually a mathematical statement. It's not a figure of speech. It's nothing like, I'm 95% confident that the Lions will win. Let's say I'm an optimist. So it's not a figure of speech. It means it speaks to the methods that we use to come up with this confidence interval. And the methods that we used will give us a correct confidence interval 95 out of 100 times. So it's based on how we developed this confidence interval through that algebra that we went through. So we're picking this 1.96 because it's a 95% confidence interval. So what that means is that if we took samples, so this problem gave us one sample. It said a random sample size 36 has a sample mean of 20. Well, see how that 20 went right here into the formula? If we took a different sample, we probably would not get exactly the same thing, right? We'd get a different mean. So every sample, like if we had, maybe the other sample had 19.3, so we put 19.3 here for 20, this is going to be a different number, right? So there's nothing magical about this confidence interval. It comes from the sample, but because of the way we came up with this process, checking to make sure that our x-bar distribution is normal, for instance, because of the way we did that, if we take 100 samples, 95 of them will give us an interval that is true, right? It'll give us a true statement. 95 of them will. 5 of them will give us a false statement, and we won't know which one is which. So all we can say is, here's our confidence interval. We came up with it from our one sample. We just had the one sample with a mean of 20. And with that sample, we came up with this confidence interval. So we are 95% confident that this interval here is one that contains population mean mu. Do we know it contains population mean mu? No, we don't. This could be a false statement. It could be that 20 was a really weird sample. And when we use this really weird sample, we got something that wasn't true. Maybe the mean of the population is actually 25, and we just got a really weird sample, so we get our confidence interval here and we're wrong. The mean is not in between here, the mean is actually 25, right? So we will occasionally get a mistake, but because we're sampling from a normal distribution, right, our sample size was big enough so that we know that this X bar distribution is normal, which means that probably 20 is not going to be a crazy z-score, right? I mean, there's a 99.7% chance that 20 will have a z-score of negative 3 to 3, right? So it could be an outlier. It could be a really just weird sample that gave us a confidence interval that's not true. But based on how we set it up, 95 out of 100 times, we're going to get a mean that will give us a correct confidence interval. Now, it doesn't mean that population mean is right in the middle here. The population mean, maybe it's 17.2, like it just barely made it, right? It's way on this end, but it made it. So when we say we're 95% confident, we're speaking to the method that we use that will work 95 out of 100 times. Sometimes people say we're 95%, or they'll say there's a 95% chance, and then all the rest of the wording is the same. There's different ways you can say this, but because we get tripped up on the wording a lot, I'm going to be very consistent and say it the same way every time. And just remember that this statement is not a figure of speech. It's a mathematical statement. It's a precise statement. It means that our technique will give us a true confidence interval 95 out of 100 times, even though we won't know if this is one of the 95 good ones or one of the 5 bad ones. We don't know. So we can just say we're 95% confident that this interval is one that contains population mean mu. Okay, it's a little confusing process, but we'll get better at it as we go along, and if it's not really making a lot of sense yet, it will by the time we're done. So here's one thing that we cannot say, and this is a really easy thing to get mixed up on. So, okay, software sometimes doesn't cooperate. So here we go. Here's what we can't say. I'm going to put this no in red. I just write something and then we'll talk about it. So here's what we can't say. We can't say there's a 95% probability that mu is between 17.06 and 22.94 because mu is not a random number. Mu is a constant. Mu is either between these numbers, which means there's a 100% probability, or mu is not between these numbers, which means there's a 0% probability. We just don't know which. So it's sometimes when students first see these interpretations, it's like this doesn't seem like a very strong statement. But that's the strongest statement we can make because we really don't know what the population mean is, right? So we don't know if our confidence interval captured that mean. All we can say is we're 95% confident that it did, but we definitely cannot say anything about probability. There's not a 95% probability that it's between here. There is either a 100% probability because mu, that would mean mu is between these numbers. Maybe mu is 20. If let's say mu is 20, then I could say there's a 100% probability that mu is between here, right? If mu is 15, I'd say there's a 0% probability that mu is between here. But the thing is, we don't know where mu is, so we can't say anything like this. So we don't want to say this. So again, just to make it official, mu is either between these numbers, and if it is, then the probability is 1 that is between them, or mu is not between these numbers, in which case the probability is 0 that it is between them. We just don't know which. So we can't make this statement. We can only make this statement above. Say we're 95% confident. Okay, so you don't want to say anything like that. But we could say, well, why would we want to be 95% confident when we could be 99% confident, right? I mean, we could do the same process we just went through and use a different z-score to be 99% confident. So if we were to do that, we go back to the formula. You know, the same formula we used above. And we've got less than x bar plus e. And we need to find e. Well, if we're going to be 99% confident, then you look on that little table, and the z-score here is going to be 2.58. Right? That's going to be our critical value. So our maximum margin of error would be 2.58. All the rest of this would be the same, 9 over the square root of 36, which give us 3.87. So we've got a different maximum margin of error. Now the mean is still going to be 20, right? So if I go through the same math, we would get 20 minus 3.87 is less than the mean, which is less than 20 plus 3.87. And then when we go through here, what we get is 16.13 and 23.87. So if you look at our new confidence interval, you may notice something that's not as good when you compare it to our old one. So here's our old one up here. We were 95% confident about this one. Well, here we're more confident. But what's the trade-off? We're more confident, but what happened? This is just a wider interval, right? So that's the trade-off. We can be more confident, but we're less precise. So that's the trade-off here. So make a little note here. We are more confident, but we have a wider interval. So we've lost some precision. We are less precise now. Whoops, there's a missing C. There we go. Less. All right, let's do this right here. We're less precise. Okay, so what if you're thinking, okay, 95% confident, we get this interval, 99% confident, we get this interval, but what if you're like, you know what, I don't want to play around with this, I want to be 100% confident. And you can be, but as you imagine, there's going to be a little bit of a trade-off here. So to do this, we're going to have to find a z-score. We'll have our z sub c. To be 100% confident, our decimal, which we had before, was 0.95, then 0.99, and now it becomes 1. And the only way you can get all the area under the normal curve is if your z-score is infinity. So when you plug infinity into the formula for E, because basically, remember before we had, for instance, 0.99. We used 0.99, and it gave us a z-score of negative 2.58 to 2.58. Well, now we want to go even further. We want the whole thing shaded. Well, that's going to take us from negative infinity to infinity. So when you plug that in your formula for E, you're going to end up with this z-score, or you're going to end up with this confidence interval that goes like this. And you can say, yes, I'm 100% confident that it's in there. but you have zero precision, right? Completely gone. So it's not very informative. So we were, like I said, usually we're going to be, instead of being 100% confident, we're going to be either 90, 95, or 99. But there's always a trade-off. The more confidence you have, the less precision you have. And that's what this next little paragraph here is about. So it just says, we have more confidence in the 99% confidence interval, of course. But it's just because the confidence interval is wider. Okay, so that's just a little summary of what we just did. And then we've got this little confidence level addendum that I started to use because I seeing that it's still sometimes kind of a tricky concept to get a hold of. So we've got this confidence level addendum we can look at. So we know that a confidence level of 95% implies that 95% of all the samples would give an interval that includes mu, or whichever population parameter is being estimated, and only 5% of the samples would yield an erroneous interval. Let's suppose we have 200 random samples of 40 GRCC students. So we're looking for the mean age. So think of it as like we've got all the GRCC students. So each semester we have about 15,000 students. So let's just say, think of this population as just being a whole bunch of numbers. It's about 15,000 numbers. We're trying to figure out the mean age of a GRCC student. We've got 15,000 numbers in here. And so we take samples of 40 students, right? And so we get this sample size 40. And let's say we find the sample mean here is 26.8. Then we get another 40, another sample. Maybe the mean of this sample is 24.4. And we just take a bunch of these samples so that we take 200 of these random samples. And because they're randomly selected, we're going to get different numbers for the mean, right? We get a bunch of different numbers for the mean. And every time we create a confidence interval, it's going to be based on this sample mean. So these are going to give different confidence intervals for each sample. So let's say using sample 1, we create a confidence interval. We get 24.8. Less than the mean, which is less than 28.1. And then think of this as a number line here, 20, 25, 30, 35. And I'm just going to plot this on the number line in interval form. So this one is like 24.8 to 28.1. So maybe it's right in here. We're saying somewhere in here. So based on that first sample, we think that somewhere in here in the number line, we believe that the population mean is in here somewhere. So maybe it's like right here, maybe it's over here, maybe it's in the middle, but we did a confidence interval of 95%, so we think it's probably in here. And let's say we go right down the line here for all 200 samples, and we just come up with these different confidence intervals. So they're all going to be a little different. So maybe this one is over here, it gets here, and then we just keep doing these. There's just slight variations on all of these. And we just keep going a few more. And go something like this. And then let's say somehow we find out later on that, oh, you know what, the average age is actually 27. So we've got this like 27. That's actually the mean of the population is 27. So then we look at our samples, and you look down here, and most of these samples gave us a confidence interval that actually captured the true mean. But if you look at this one missed, right? So this sample 5 must have been kind of a weird sample, and it was a little bit high. So maybe just, through random sampling, some of these samples just going to be a little weird? And you typically just get one sample, because normally you have to pay somebody to come up with a sample. It's not free, right? You have to some research firm will get your sample for you, and you have to pay them, so you get your one sample. And with your one sample, you come up with your confidence interval. This particular sample happened to miss it. So this one right here missed it. And again, this is not the case what would happen, because normally you would never know what the population is, right? You don't get that information. So this is just showing that with a 95% confidence interval, 95% of these are gonna give us one that works, even if they barely make it. Like, I mean, this one, I guess this one is towards the right end of their confidence interval, but 95% of them will capture it. So out of all of these samples, you have 200 samples you take. Out of those 200 samples, 95% of these samples would give an interval that contains mu. Right, 95% of them would, 5% of them wouldn't, and the key is we don't know which is which. So that's why we make that statement, we're 95% confident, because normally we're going to get an interval that captures the mean. You know, most of these do capture the mean, some of them don't, and we just don't know if ours did or didn't do it, right? We don't know. So this just says approximately, in this case would be 190, because there's 200, 190 of these samples, right? 95% of 200, right? 95% of 200, there's 200 samples. 95% of them will capture the mean if it's a 95% confidence interval. So approximately 190 of these samples give an interval that contains the population mean mu, and approximately 10 of these samples give an interval that does not contain the population mean. And the important point is this, is that we don't know which of these intervals actually contain the population mean. So that's what a confidence level gives us. It's just, confidence level is the percentage of all possible intervals that can be expected to include the true population parameter. And we're not going to know if it actually includes it or not. We're just going to know that it probably does. Right? If you use a 95% confidence interval, 95 times out of 100, you're going to have an interval that contains the true population mean, or whatever the parameter is. Okay, so there's actually a way to do this on the calculator also, which I'll show you here. And this is just to check. So in a first year stats class, we have to build these from scratch all the time. But there is a way to do it on the calculator. I'll show you that. Just so, again, usually if I don't show it, students will just do everything on the calculator and do really no calculations and say, well, you didn't say we couldn't use a calculator, right? So I'll show you how to do it on the calculator, but then I'll say, but we have to still do it by hand. We have to build these from scratch. Otherwise, 3 days after you do it, you have no idea how to do it, because you just sort of had the calculator do all the work. But it's a good way to check. So I'll give you the basic command here. You go to your stat menu, or the stat button on the calculator, and then we're going to go over to tests. And then we go to one that's called Z interval. And Z interval because it's Z scores, and we're using confidence intervals. Then from there, there's a couple of branches. There is data. If you actually have your data stored in a list, you choose data. Otherwise, you choose stats, which is what we would do here because we don't have the original data, right? So we would press stats. So I'll do this one, show you how to do it on the calculator, but remember, this is only to check, right? We need to be able to develop these by hand. We need to be able to start at x bar minus e is less than mu, which is less than x bar plus e, just like we did. But this is just a check. But I'm going to show you on the calculator doing that same problem. Okay, so we go over to the stat button, and we go over to tests, and we want the one that says Z interval. So go down to Z interval, and then here's where it's going to ask us if we have the actual data or not. So we don't have the actual data. If we did, see where it's looking in list 1. So it would look there, but we go to the stats and hit enter, and then we input what we've got here. So the standard deviation for this one is 9, the mean is 20, and n is 36, sample size 36. And then the confidence level here, what we want to do is, this one was a 95%, so you go 0.95 and then calculate. And there's no fun, right? Did all the work for us. Not fun at all. Came up with the same numbers. You can see right there, we've got the same numbers that we got. So this is just for checking, right? We need to be able to develop it by hand, but if you want to check, that's how you do it on the calculator. Another topic that we need to look at in this section is finding the sample size. So in the design stages of statistical research, we'll have to decide in advance on the confidence level we want to use, and then select the maximum margin of error. So how we make these decisions depends on the requirements of the project and some of the practical issues that you'll run into. But whatever we come up with, we have to next determine the sample size. And we've got a formula to help us do this. So we've got our formula here. We've got our critical value, our z-score, sigma. We've got a specified maximum margin of error. So in the problems that we look at, they'll give us our margin of error. And then here's what we have to remember. This always gives us trouble. So we have to remember that we are finding a sample size, right? So think about what we're doing. This is not just a formula we plug in, get a number, and don't think about it. This is a sample size. If we're figuring out the number of students we need to interview, right, to figure out the average age of a GRCC student, or whatever it is, n has to be an integer, right? It's got to be an integer. If I say n equals 17.3, that makes no sense. That makes it sound like I don't really know what n is. N is a sample size, so n is going to have to be an integer. And then the note here says, if n is not a whole number, increase n to the next highest whole number. So pretty much the thing to focus on is increase n. It doesn't say round, it just says increase n. So it's because this is a guarantee theorem. There's a theorem and that's a type of theorem that says that for this to work, it could say, like, let's say we get 17.3. That means that for this theorem to work, we need 17.3 samples. It means 17 samples is not enough, right? We need 17.3. Well, we can't ask 17.3 students, so we need to ask 18 students, right? So that's what it's getting at here. And the other note is just that we can actually derive this formula from E. So we have a formula we've seen a few times here, Z sub C times sigma over the square root of n. So just to do a little algebra here, we know that really, Z sub C is a number, right? It's just some number. So algebraically, Z sub C times this is the same as Z sub C over 1 times this, right? Because it's just some number like 1.96. 1.96 over 1 is the same. I'm just doing it like this because then we have a fraction times a fraction and we multiply straight across. So that would give us E equals Z sub C times sigma over the square root of n. So if we want to solve this for n, we could get rid of the fraction by multiplying both sides by the square root of n. Right, so that would cancel. And we get E times the square root of n equals Z sub C times sigma. So if we want to get n by itself, we could first divide each side by E. that would cancel. That would give us the square root of n equals z sub c times sigma over e. And then if we just want to get n by itself, to undo the square root, we just square both sides. And then that square cancels the square root. They're inverse operations. So we get n equals z sub c times sigma all over e squared. So that is where this formula comes from. So to figure out the sample size, we just plug this in, and remember that it's a guarantee theorem, so it's like says it's guaranteed to work if the sample size is this. And so it's got to be an integer. So if we get a decimal answer, which we will because we got a square root, right, it's just never going to end up being a whole number. So whatever we get, we just move it up. We don't round, we just always increase to the next highest whole number. So this example on page 370, number 14 from section 7.1 homework, says, suppose x has a normal distribution with a standard deviation sigma of 1.2. And then part A says, find the minimal sample size required so that for a 90% confidence interval, the maximum margin of error is E equals 0.5. So they want us to find the minimal sample size required. The minimal sample size, right? That's what our formula is going to give us. So we've got n equals z sub c times sigma over little e squared. All right, so a 90% confidence interval. So we need to look on that little chart again, or the one that's in the inside cover of the book, or wherever a standard normal curve is shown in your book, wherever the tables are. And of course you could use a calculator too, but it's just more work. So like we talked about earlier, if you look on that table, you'll see for a 90% confidence interval, the critical value is going to be 1.645. So z sub c for this one is 1.645. So hopefully you can find that on that little, it's like the little table on the inside front cover. I brought it up in the video a couple of times, and it just shows the confidence interval critical values. And if you look on that table for 90% level of confidence, your critical value, or in other words your z-score, is 1.645. So we plug that into the formula, we get 1.645. Sigma was 1.2. And the maximum margin of error, E, they said in this case is going to be 0.5. Then we have to square all of this. And from here, you just let the calculator do the work, and you should get right around 15.59, which means that for this level of accuracy, so this margin of error, in a 90% confidence interval, we need a sample size of 15.59. Now a sample size is going to have to be an integer, so this doesn't make any sense like this. So we move it automatically to the next one. We're not rounding. We're just going to say we need 16 samples, right? We need 16 samples to make that work. And it's not because I rounded, because even if this said 15.09, I would still say 16, right? Because basically our formula is saying, well, 15 is not enough. We need more than 15. We need 15.59. So since it's got to be a whole number, we use 16. Now, in practice, probably 15 would work. But if you want to make sure it works, 16. So we're always going to just move to the next number. Not rounding, just always moving up. So we need 16 samples here. Okay, then this one goes on. It says for part B. Part B says check the requirements. Based on the sample size and the X distribution, can we assume that the X bar distribution is approximately normal? Well, so we look at this and you might say, well, 16, that's not enough, right? A sample size of 16 doesn't meet our criteria of 30, right? But in this case, it doesn't matter because look up here, X is normal. We're sampling from a normal distribution, so this doesn't matter any size. Even a sample size of 4, right, would be normal. So since X is normal, the sample size of 16 is just fine. So we know the X bar distribution will be normal because the X distribution is normal. But if it didn't say this, if we didn't know that X were normal, then we couldn't, using a sample size of 16, assume that X bar would be normal, right? So if this isn't here, for X bar to be a normal distribution, we need 30 or more. But since X is normal, we're okay. So to answer this question, we can just say yes, the original distribution is normal. The original distribution is this X distribution that they said is normal. So the original distribution is normal. So the X bar distribution will also be normal. So that's how you use that formula. So there'll be a few of them in the homework for us to look at. But now I want to look at one problem, a pretty decent problem, problem number 16, where it just gives us the kind of problem you're going to run into in 7.1. And we'll go through all the steps A through D, which is pretty much what you'll have on the homework, and just walk through this one so you can see one of these done all the way through so you'll know how to work on the homework problems. So with that, let's take a look at problem number 16 in this section in the homework. And problem number 16, this one is on page 371. And it's talking about uric acid. And this one just says, let's see, overproduction of uric acid in the body can be an indication of cell breakdown. This may be an advanced indication of illness such as gout, leukemia, or lymphoma. It says, over a period of months, an adult male patient has taken 8 blood tests for uric acid. So I'm just going to write down some of this. So N equals 8, right? 8 blood tests, you got a sample size of 8. It says the mean concentration was X bar equals 5.35 milligrams per deciliter. And it says the distribution of uric acid in healthy adult males can be assumed to be normal. Okay, so X is normal, right? We're sampling from a normal distribution. And also sigma equals 1.85. So this is the standard deviation, population standard deviation, 1.85 milligrams per deciliter. And again, remember in section 7.1, we're in this fairly unrealistic situation where we don't know mu, but we know sigma, right? So like I said earlier, in 7.2, we'll get the more realistic situation where we don't know this either. But for 7.1, we happen to know sigma. Also, we know that the X distribution is normal. So we're sampling from a normal distribution. And from that normal distribution, we have a sample of size 8. And this is our sample mean from those 8. So then part A says, I'll do this over here on the right. Part A says, find a 95% confidence interval for the population mean concentration of uric acid in this patient's blood. What is the margin of error? When they say margin of error, that's just big E, whatever that is, right, when we find it. So we've got a 95% confidence interval. So we can find the critical value, right? We can find our Z sub C for if C is 0.95. And that is going to be 1.96. And that's just from looking on this on that little table. Or if you wanted to, you could go inverse norm. It's a little trickier Because remember, you're going to have to go inverse norm 0.025 because it's half of 5. And then you have to not use the negative. So it's just much easier to do it with that little table. Maybe I should just mention, just to make sure we're clear here, this number came from that little chart that we've talked about. If you really wanted to do this on the calculator to get these z-scores, if you want 95% to be inside here, so you got 0.95, you need to find these two z-scores, and there's symmetry here, so they're going to be the same number. One will just be negative. So we would take that 0.05 that's left, right? 0.05, because there's some of it here, some of it here. So we'd have to divide that in half to get 0.025. So there's 0.025 here, 0.025 here. And then to find those z-scores, you go inverse norm. So if you're going to find this one, we'd punch in 0.025. But we just have to remember that if we do it like this, we're going to get a negative z-score. And when we plug it into our formula for E, we always use positive. That's why it's just easier really to use a table, because you don't have to cut this in half, and you don't have to remember to use the positive value instead of the negative. Do this on the calculator, and if you round, so you get negative 1.96 rounding. But then remember, when I plug it in the formula, to not put the negative, right? So it's a lot more work on the calculator. But if you really want to use the calculator, that's what we'd have to do. Or you could just punch in inverse norm and add the 0.95 to the 0.025 to get over to the positive 1.96. And then you don't have to worry about the negative, getting rid of the negative. But again, all this right here, we don't really need to do. We can use that little table and get this right from the table. So then for part A, we need to use I want blue here, x bar minus e, x bar plus e. So we know x bar, they gave us x bar, so we need to find e. And now that we have this, we can find e, because e is going to be z sub c sigma square root of n. Z sub c is 1.96, and sigma, it said, is 1.85, and then over the square root of 8. Right, they gave us sigma, sample size is 8, and if you do that, you will get about 1.28 for our maximum margin of error E. So for part A, it says, what is the margin of error? The margin of error, you could just say, is 1.28. But really we want to use this to find the confidence interval. So we take 1.28, plug it in for E here and here, and we use 5.35 for x bar in those two spots. So we would go 5.35 minus 1.28 less than mu less than 5.35 plus 1.28, and we get 4.07, 6.63. Or we could say something like 4.07 milligrams per deciliter to 6.63 milligrams per deciliter. However you want to say it is fine. I usually just go with something like this. Sometimes it's nice to have the units on there too. You could put the units on here. But basically these are the numbers we're looking for. So here is our confidence interval. This is a 95% confidence interval. Here's our margin of error, 1.28. And then part B says, what conditions are necessary for your calculations? Well, for us to do this, we have to be sampling from a normal distribution, right? Because our sample size is not 30 or more. So we got a small sample size, which means that the way we can guarantee that X bar, that this sampling distribution is normal, is that we were sampling from a normal distribution, which we were, right? X is normal. The X distribution is normal, which means the X bar distribution will be normal. So for part B, we can just say that the distribution of uric acid concentration, and that's our X, right? That's our distribution we're sampling from, is normal. So know that that distribution is normal because they told us it was, and also we know sigma. We'll find out in 7.2 that if the first part is correct, but we don't know sigma, we have to use a different type of distribution. But for now, we're gonna, in 7.1, they're gonna give us sigma, and they tell us this right in the problem. It says that, let's see, where is it? It says the distribution of uric acid in healthy adult males can be assumed to be normal. Okay, so that takes care of part B. So for part C, this is the part that we tend to struggle with. Part C says, interpret your results in the context of the problem. So I'm going to start off with the same wording as always. I'm going to say, we are 95% confident. And remember, this is not just a everyday figure of speech. It speaks to the process we're using. It's a mathematically precise statement that says if we repeat this process, or if we do this process 100 times, take 100 samples, 95 of these samples will yield an interval that captures the true population mean. So some of you guys may have taken AP stats or some other stats class, and there's another common way to say this is there's a 95% chance. But I'm just going to say it the same way all the time, just so it makes it a little easier to learn. So I'm going to say we are 95% confident that this interval, I'm just going to write down the interval, and I'll put the units in it this time. You don't have to, but it'll just make it a little easier to make sense of it in the context of the problem. So we're 95% confident that this interval is one that contains the population mean mu. At this point, it says, if you look at the question, interpret your results in the context of the problem. So we need to say what this mean mu is in the context of the problem. And a lot of times the easiest way is just to look at the question. So 16a says, find a 95% confidence interval for the population mean concentration of uric acid in this patient's blood. So I'm going to use the book's wording because it's just easier to do it that way. Population mean concentration of uric acid in this patient's blood. A couple of things here. So I put population mean mu, right? It looks a little redundant here, and it is, and I'm just doing it because if we're not careful, sometimes students will write population mean X bar, or they'll write sample mean. We're not trying to predict the sample mean. We have the sample mean, right? They tell us the sample mean was 5.35, so we want to predict the population mean mu, right? Population mean. So that's why I just write it here just to make sure we're talking about the population mean and everybody's aware of that. Other than that, another thing that can happen is the wording here. So we can't say we can't say population mean concentration of uric acid in healthy adult males. That's not what we're talking about, right? Look at the question. We're looking for the population mean concentration of uric acid in this patient's blood. So again, I mentioned this quite a bit, but we have to pay attention to all the details, right? We can't be sloppy about this. So we are using our sample mean to make a prediction about the population mean. And in this case, the population mean is the population mean of uric acid in this particular patient's blood. Okay, so we have to be a little careful about the little details, of course. And that's how we interpret the results. So when you interpret the results, this step is pretty much automatic. We are 95% confident. This could change, but that first statement is pretty much the same for most of Chapter 7. 7.1 and 7.2 are both talking about population mean, and 7.3 is population proportion, but it's very similar. So for any of those problems, our conclusions can start off with a statement just like this. We are 95% confident. Then we can say that this interval, list our interval, is one that contains population mean. So we'd say mean in 7.1 and 7.2. 7.3 would just say population proportion. So all that is the same. And then this last part just says what this thing is in the context of the problem. And that's pretty much what you can use on that format. Works on any of these in Chapter 7. Okay, so they take a little practice. The wording, this part C will give us the most trouble. Just generally speaking, this is the part that we get tripped up on. So it just takes a little practice. And you don't have to word it exactly like I am. I'm just giving you a framework that will work. You can word it differently. Just remember, you have to be a little careful, though, because we're still looking for the population mean, right? Not the sample mean. So just be a little careful. And then finally, for part D, they ask, find the sample size necessary for a 99% confidence level. Whoops, reading the wrong one. Find the sample size necessary for a 95% confidence level. So in a 95% confidence level, with a maximum margin of error E of 1.10 for the mean concentration of uric acid in this patient's blood. So here's a question we should think about. Look what we had over here. We had a maximum margin of error of 1.28. Here, we want a smaller margin of error. So if we're going to get a smaller margin of error, are we going to need more samples or less samples? And hopefully you're saying more samples. So we had 8 samples before, and we had a margin of error of 1.28. If you want a smaller error, we need more samples, right? In fact, if you wanted this error to be 0, we'd need all the samples. Wouldn't we have 0 error, a margin of error 0, if our sample was the entire population? There'd be no margin of error because we'd actually have the real answer, right? So just generally speaking, if we want a smaller margin of error, going down from 1.28 to 1.10, we're going to need a larger sample size. So we should expect our answer to say more than 8. But now we can just check and see. So we use our formula here. Plug in our values. So 95% confidence level gives us a z-score of 1.96. And we know that sigma is 1.85, margin of error 1.10, and we square this, which gives us roughly 10.87. Make sure you don't forget to square. It's kind of an easy mistake to make, is to forget to square this. So do these calculations, hit enter, get a number, then square it, which means that we need 11 samples, right? So remember, we're looking for n. N is a sample size, so the answer has to be a whole number. 10.87 isn't big enough, so we need 11. Again, when it comes to sample size, we don't round here, we move it up. This is saying 10 is not enough, you need more than 10. but we can't have 10.87 samples, so go to 11. But remember, even if this said 10.17, we would still need 11, because it's still saying 10 is not enough. So we need 11 samples for that one. Okay, so there's a lot of information in 7.1. There's not much more information in the rest of chapter 7. It's the bulk of it is right here. So it's a little bit of a longer video. But take your time, try 7.1, and of course, let me know if you have any questions.